This video is for pages 3 and 4 from our conceptual packet. So looking at number 8, right, we've talked about a problem like this before. Notice that over here, right, I've added in that block A is sliding across a table and there would be friction, right, because it's on a table. So therefore, on my force diagram, right, I have this force of friction acting on it, but it has to be smaller than the tension, right, because it's going to accelerate to the right. And then I know for block B that the weight pulling down has to be smaller than the tension pulling up, because again, that's going to accelerate down. So make sure, right, that you have your tension greater than your friction, and in this case that you have your weight B greater than your tension. And of course, normal force and weight A should look the same. So part 9, identify what force is causing block A and B to accelerate. So in this case, remember, we are going to consider our system is going to be both objects together. And so if we are using all of this as our system, then our tensions are internal forces and therefore are irrelevant. Our weight A and our normal force, because those two are equal to each other, they cancel out and don't cause acceleration. So the only forces that are affecting the acceleration is the weight of object B is pulling down and friction is resisting that motion. So B is causing the acceleration, A is resisting, so both of them together are going to cause the net force that will cause mass A and B to accelerate. Going to Newton's third law, these ones can be pretty tough. We want action-reaction pairs, right? So if the bat hits the ball, what's the reaction force? It's always going to be switch these two terms, right? If it's force of bat on ball, now it's force of ball on bat, right? And so it's on the bat, so the force is drawn pushing the bat. This is on the ball, so it's pushing on the ball. So if you look at 11 and 12, they get ridiculously crazy. I'm sure I would be shocked if any of you had all of these forces, and I was kind of halfway through them going, oh my gosh, what's happening? So I paired them up with colors. So if you're looking, right, look for colors that are the same, right? The ground pushes the boy up, right? So what does the boy do? Where is it? Right, the earth is pulling the boy down because he has weight, and then so what is the boy doing on the earth? Right, he's pulling it up because they both have weight and therefore they both have mass, so they're attracted to each other. We know that the ground is applying a normal force that pushes up, so that means that his feet push back down on the ground. So you've got to go through and you have to identify all of these forces that are equal and opposite, right? The let's see, where's another good one? Okay, how about this one? The boy on the earth, right? He's pushing back with his feet on the earth, and so what does the earth do? The earth pushes the boy forward, and that's going to be what causes him to accelerate. So you can see in both 11 and 12, there is going to be a lot of different forces that are acting on those objects that are counteracting each other. But they're equal and opposite, and they're always in different directions. And if you ever get tricked into thinking one of those objects won't accelerate, just look at one object by itself. If I just look at the boy, right, the force that the earth is pushing is greater than the wagon that's pulling him backwards, therefore he can accelerate. Right? If I look at, let's say, just the wagon, right? Those are the forces that determine whether it's accelerated or not. So the boy is pulling on the wagon, and friction is resisting. Well, if the boy pulls harder than friction resists, then the object accelerates. So looking at our second page, right, we have a couple questions to go through. I think the explanations here hopefully are going to help. So you find yourself in the middle of the frozen lake, right? What are you going to do? Well, using Newton's third law, we know that, right, for every force there's an equal and opposite reaction force. So if you apply a force on the rock, right, the rock is going to apply a force on you, and therefore if you just think about what's happening to you, right, you have weight, you have a normal force, and the rock is pushing back on you, therefore this force is going to cause your mass to accelerate. So you could hopefully then slide to the edge of the lake. Number 14, if an object is at rest, can you conclude that there are no forces acting on it? Well, we know that from Newton's first law, right, we know that an object at rest will stay at rest, but it's not going to stay at rest if there are no forces. It's going to stay at rest if the net forces are zero. So, like we've gone through multiple problems, you could be pushing an object. There could be friction that's counteracting that, that's equal and opposite, so those are zero. Your object would have weight, and then maybe a counter was pushing it up. Right? There's four things outside of that object that are pushing and pulling it, but all of them add up to zero, therefore it's going to stay at rest. Okay, so let's look at number 15. If a force is exerted on an object, is it possible for that object to be moving with a constant velocity? I'm not sure why I have no here. I'm going to change that to a yes, as my answer key shows. So yes, according to Newton's first law of motion, the object will move constantly if the net force is zero. And just because there's a force exerted on the object, right, if other forces are counteracting that force, right, if multiple forces are acting on it, then they can cancel each other out, and therefore it's not moving. Or moving at a constant speed. And our last one, right, number 16, a hollow tube forms 3/4 of a circle, right? As the ball emerges from the other end, does it go A, B, or C, and justify your answer? Well, the reason why it's turning, right, is because there's a force that's making it accelerate. We know that if it has a constant velocity, we know that the acceleration is zero. But in this case, because it's turning, remember that velocity is speed and direction. So because the direction is changing, there must be some sort of force that's causing it to change velocity or accelerate. So that's why it turns in a circle. But as soon as it gets to the end of, see if I can erase my drawings here. As soon as it gets to the end of the picture or the tube, there's no more forces, so therefore it's going to go in a straight line because of Newton's first law. Right? It has inertia, and because it has inertia, it will travel in a straight line at a constant velocity until some force causes it to turn. So it won't keep going at A or B, it's going to go straight.